So today we will be talking about buoyancy, which is the weight of fluid displaced. To do this, we will have a log that is in water. It has some radius r, a length of L, and then we have a height here of h. H is going to be the vertical distance from the h. What we'll be doing is deriving an expression for the specific gravity of our log as a function of this height h over our radius, when this vertical distance between the surface of the water and the highest point on our cylinder is less than our radius. So then, back to our original equation, the weight of water is going to be the density of water times the area times the length times acceleration due to gravity, which is equal to the weight of the log, which will be the density of the log, times the area times length times gravity, acceleration due to gravity. Weight is equal to mass times gravity, and mass is then equal to the density times a volume. So replacing mass into this equation, we get weight equals density times volume times gravity. Volume is equal to area times length. So using this, we can then plug in that weight equals density times area times length times acceleration due to gravity. Since buoyancy is the weight of our fluid displaced and water is the fluid that is being displaced, our weight for water is going to be equal to the weight for the log. The area for our water is going to be this cross section of the log right here. So this is our area for the water. The lengths on both sides will cancel out, and so will the acceleration due to gravity. And the area for our log can be replaced with pi r squared. So what we get is the density of the water times that cross-sectional area is equal to the density of our log times pi r squared. We now need to find this cross-sectional area A. So to do that, we will start by drawing a diagram with the radius r, and we'll draw in our height, or our h value, which is the vertical distance between the water surface and the highest point on our cylinder. This is going to be equal to r, our radius, and this line is also equal to our radius. We can then draw a line here, which will be the radius minus that vertical distance h, and we get two 90-degree triangles. We will call this angle theta. We now need to find this portion of the triangle, which we can use using the formula a squared plus b squared equals c squared, where this will be our b squared. So b will equal to the square root of c squared, which is our hypotenuse r, minus a squared, which is this height here, which is r minus h. So b, this portion right here, is going to be equal to the square root of r squared minus r minus h squared, which can be simplified to the square root of 2, the radius times that vertical distance h, minus h squared. Since there are two triangles here, we need to multiply this by 2 to now get this total length, which will be, I guess, b plus b, or the base of the entire triangle. The height of our triangle is going to be equal to the length of this line here, which we already know is the radius minus that vertical distance between the surface of the water and the highest point on our cylinder. So using this base times the height, we will find the area of the triangle, which is going to be equal to 1/2 base times height, which is equal to 1/2 times our base, which is 2 square root 2 radius times that vertical distance minus the vertical distance squared times our height, which is radius minus the vertical distance. And these 2's will cancel to give us the square root of 2rh minus h squared multiplied by r minus h for the area of the triangle. The area of a circle is then going to be equal to pi r squared, but in our case, r is going to be capital R, so pi r squared. So then next we need to find theta, which we will do using SOHCAHTOA. So the cosine of theta is going to be equal to the adjacent, which is r minus h, over the hypotenuse, which is r. So then theta will be equal to the inverse cosine of r minus h over r. And then since there are two thetas, we have to multiply this by 2. We will use all 3 of these to find this area that is above the surface of the water. Our area above the surface of the water is going to be equal to 1/2 theta times 2 because of the 2 triangles over pi, which will be multiplied by the area of the circle minus the area of the triangles. So using the equations that we found on the last page, our area above is going to be equal to 2 cosine to -1 times, or r minus h over h over 2 pi times pi r squared minus the square root of 2rh minus h squared multiplied by r minus h. This 2 and this 2 will cancel, and then this pi and this pi will cancel, and that simplifies to r squared, the inverse cosine of r minus h over h, minus the square root of 2rh minus h squared multiplied by r minus h. So using this area above and the formula for area of a circle, we'll be able to find the area underneath the level of the water, which will be the area under equals the area of the circle minus the area above. So the area underneath will be equal to pi r squared minus the quantity r squared, the inverse cosine of r minus h over r, minus the square root of 2rh minus h squared times r minus h. So going back to our original equation of the density of the log times pi r squared is equal to the density of the water times the area underneath the surface. Specific gravity is going to be equal to the density of the log over the density of the water, which is going to be equal to the area underneath divided by pi r squared, which is all equal to the specific gravity. So because of that, to find the specific gravity, we need to divide up here by pi r squared. So divided by pi r squared. Doing that will then give us the specific gravity is equal to 1 minus 1 over pi inverse cosine times r minus h over r minus 1 over pi r squared times the quantity of the square root 2r h minus h squared times r minus h. We can then simplify this portion, so what we'll get is 1 minus 1 over pi inverse cosine -1 of 1 minus h over r, and then minus the square root of 2rh minus h squared times r minus h over pi r squared. Since we need to get this in terms of h over r, this term and this term are already all right, but this one needs to be multiplied by r squared over r squared to get it into terms of h over r. So what we will get when doing that is the specific gravity is going to be equal to 1 minus 1 over pi inverse cosine of 1 minus that vertical distance over our radius, then minus 1 over pi r squared times r squared, the square root of 2, and then h over r minus h over r squared times 1 minus h over r. These r squares will then cancel out, and what we get is that the specific gravity of our log is equal to 1 minus 1 over pi times inverse cosine of 1 minus that vertical distance over r minus the square root multiplied by 1 over pi of 2h over r minus h over r quantity squared times 1 minus h over r. So using the equation that we previously derived for specific gravity, we are now going to find the value of h over r for a specific gravity of 0.8. We'll use that using Google Colab, and we'll also make a graph of how specific gravity corresponds to the h over r values. So what first we are going to do is we are going to import some math functions. So this will allow us to use the arc cosine that we need from the previous equation, and then also it'll allow us to use the square root. So .optimize, and then import root scalar, and then import plotly.graph underscore objects as go, which will allow us to have a graph of our data. Plotly.io as PIO. So in this next portion of code, we're going to define h over r, which we're going to write as hr equals to np dot line space, which is going to make it an array going from 0 to 10 in increments of 1. And then we are going to define our specific gravity, and that is going to be SG equal to the equation that we found in the first half of this video. So 1 minus parentheses np dot arc cosine is going to give us the arc cosine that we need. 1 minus hr, close the parenthesis, minus np dot sqrt is going to give us our square root of 2 times hr minus hr, the double asterisk will make it squared, close the parenthesis, multiply that by 1 minus hr close the parenthesis, and then we're going to divide that by pi. And we'll be using a new block of code, and that will be making our graph, everything that we type in this block of code. So this part will be making it a scatter plot with our x values equaling HR, and then the y values will be equal to specific gravity. This next part is going to be determining the layout of our graph. So first we are going to indicate the height of our graph, and it's going to be equal to 400, and the width is going to be equal to 500. You'll then do a comma and delete those parentheses. So then this next part is going to be naming our x-axis title, and it is going to be equal to h divided by r. And then this next portion is going to be our y-axis title, which is going to be equal to specific gravity. This next part is going to make our tick marks for our x-axis start at 0, and they will then increment by 0.2. Then we'll be naming our graph, and that is going to be specific gravity of a floating cylinder, or in our case a log, for varying heights h above the surface of the water level. And then title will underscore x will equal 0.5, and close the parentheses. And now we have our graph of specific gravity of floating cylinder for the varying heights above the surface of the water level, with our specific gravity on the y-axis, our h over r values on the x-axis, and you can see as the h over r values increase, the specific gravity will decrease. So now in this next portion of the code, we will be solving for our h over r value when the specific gravity is equal to 0.8. So let's start by defining this. And we're going to put our HR here, and then that. And then we'll be typing return, and we can just copy and paste our equation for specific gravity. We'll want to enclose it in parentheses so that we can then subtract the 0.8 value for our specific gravity. And then for our result, we'll want to type result equals the root scalar from earlier, and close that F bracket is equal to 0 dot comma 1 dot, close it, and then result, and we'll get our value for h over r. And then we'll get a value of 0.508 for our h over r value.